Oh, goodness. Oh. Okay. I need to tell Jesse where he sits. Okay, kids. Wait, there you are. You already came back. I'm going to have you sit 2 seats behind Evan. You saw him here. You were going to say anything.
What?
What?
Does he have? I didn't know he had a seat.
Everyone has a seat. All right. Jesse, last time you were in, I gave you the materials, right?
I think so.
Okay. Double check. The rest of you need to go ahead and get your notes out. That's a shame. So, we're going to start off this new section on motion. First of all, looking at the preview of words that I will stumble over time and time again because I tend to talk fast, as you know, and having words like tangential speed just does not flow off the tongue very well. So you'll hear me just stumble over them every once in a while, or if you hear me go tangential speed, that's me trying to prevent it, okay? We also are going to start off by looking at some examples of what we're going to encounter in this chapter, and I think it's funny. But what we're going to focus on first over the next couple of days are these objectives. We're going to solve problems involving centripetal acceleration. Solve problems solving centripetal force. And notice how I'm saying centripetal, not centrifugal or centrifugal, depending on how you say it. They are different, okay? And then we are going to explain how the apparent existence of an outward force in circular motion can be explained as inertia resting in the centripetal force. Resisting the centripetal force. So you should be able to explain that by the time we're done here. But if any of you grew up with the old school playgrounds, I'm talking about things that no longer exist, I don't think anymore, unless you go to like a back alley type of playground here. But these little things. So has anybody been on those? Say what?
Yeah, it's metal too, so you can really get sliding.
Oh, it's like one you have to have your shots on before you get on there. Excellent.
Yeah.
It's been there since before our time, so it's
wow.
really rusty now.
Is there still a wooden one at the park?
Oh, yeah. I think
I don't go to the park. So, what, Sherman or Williamsville?
I think there's one in
Really?
Williamsville and one in Sherman.
Well, I'm missing out.
Williamsville's not as good. The one in Sherman.
Yeah. That one's
Missing out.
That one's
You need to get some sort of like high-speed winch on it. Something like that. So, anyway, you see what's happening? You see the motion of these individuals, right? So this one's okay. This next one, you got to watch it again. See, this next one's, is that a cat?
Yes, it is.
He's like, what are you doing? Okay, we got to watch it again. Okay. Now, this next one's going to be great. I enjoy it. Because they put a motorcycle or a scooter.
Yeah. He came out the top, too.
Mm-hmm. So, these are demonstrating some of the concepts that we're going to be discussing in this chapter. So we're looking at circular motion in this. I know it's hard to stop watching these things. One more time. Okay. So, great. We're going to start off with my favorite word, tangential speed. Okay. So, also, you're going to want to have your formula sheet out because we're going to get into a couple, or at least one formula today. Now, when we talk about tangential speed, which is denoted as v sub t or vt, whatever you'll say, of an object in circular motion is the object's speed along an imaginary line drawn tangent to that circular path. We should see, I think there's a Hold on. I'm going back to that. Nope. I think there might be one at some. Oh, okay. So, when we are looking at tangential speed, is going to depend on the distance from the object to the center of that circular path. So I have an example of the merry-go-round. I get excited every year when we talk about this stuff, not only because I get to say tangential speed 100 times, but also because I get to draw. Okay. Trying to do it. A couple years ago, I tried to do this with actual human beings and stuff. It just didn't work.
I got you. I'm volunteering. You should do it with human beings. Is that not supposed to be more entertaining?
I mean, it is entertaining, but it's. Well, let's think about it tomorrow. Okay, because I don't have it set up or anything like that here. And plus, you have to like hold hands and stuff like that. Anyway, you've all been on a merry-go-round, right? Okay, so here's the center of the merry-go-round. And you've got out here, not too far from the center here, you've got, well, let's see, what animal do we have?
Cat.
We have a large cat. Slash dinosaur.
Dinosaur.
I got a big fluffy tail.
Dinosaur.
Okay, there's a cat.
No, it's like a unicorn too.
And
It's a good dog. That's what you were going for.
And Ty is having a great time on here. Whee! Okay. These objects, or this object, okay, that's him being pinned. He's static on here, right? Out here further is another animal. What's another animal?
A dinosaur, cat, unicorn, again.
I heard 3 of them. Was there 4?
That's what I'm getting on first.
Oh, so we heard cow. They have hooves.
Yeah, it's a horse.
See, it's got a thinner tail than a horse, and it's got spots.
The rat with the short
Ooh. There we go. Who wants to ride the cow? Who wants to ride the cow? Okay, Evan, you said it. So Evan's got longer hair now. Okay. He's holding on to an imaginary thing that goes up and down. Okay, so as this and this are traveling around, they're next to each other. Okay, if you can't tell, they're next to each other. Each revolution that a merry-go-round makes, they are meeting a certain location at the same time. Okay? At any point we choose along its circular path, those two, since they are next to each other, are meeting at that same point at the same time. Now, one thing we know is Ty is closer to the center. Evidence further. Who has to cover more distance? Evan. Therefore, who should be traveling at a faster rate? Evan. So you would be considered to have a faster tangential speed. Even though they're fixed, you have to cover more time. And that's somewhat of a similar concept to what we're going to cover. I think it's next chapter when we start talking about fluids. Okay, and have you heard of Bernoulli's principle? Well, a lot of people say that's the only reason why planes fly is Bernoulli's principle. Well, there's other factors. There is other factors. In fact, Newton also plays a role in how things fly as well. But when you have to cover a larger distance in the same amount of time, you have to go faster. There's no ifs, ands, or buts about it. So, depending on how or where you are located, that is going to affect your tangential speed. And when the speed is constant, we describe the motion as uniform circular. Okay. Now, what's neat, or we haven't got there yet, is that we typically call this centripetal motion. And we're going to define centripetal motion here in just a moment. But when we are talking about how an object is moving in a circular path, and it's at constant speed, any change of direction is called centripetal acceleration. And we can calculate centripetal acceleration by the following formula. Vt squared divided by r. Or again, tangential speed squared divided by the radius of that circular path that it is traveling. So jot that down on your formula sheet. So if we look at this image, we're not so much concerned about the first two bullet points, but what we want to look at is the third bullet point here. Anyway, what they found, if we do go over the first two, is we had a particle traveling in a circular motion. As this particle moves from A to B, again, you notice that in its circular motion at the location where A is, see how its direction is drawn as a tangent to that path? As it proceeds from A to B, that vector is always changing for that particle. And if we look at short time intervals, the velocity of the particle is actually directed towards the center of the circle. The most important thing to get from this, like I said, is that third bullet point. Centripetal acceleration is always directed towards the center of a circle. In fact, it's really called center seeking, where the opposite, centrifugal or centrifugal, is center fleeing. Okay? So centripetal is what we're focusing on right now. So if you watch this little demonstration, you'll see this in action.
The turntable can rotate in a circle about its axis, and clamped down to the turntable is a wooden 2x4. And secured to the wooden 2x4 are two glass jars. These glass jars are filled with water. Inside the water is an orange cork. The cork is tied by a string to the lid of the jar. The jar is inverted upside down, and the cork is floating within the water. What I'm going to do is spin this turntable. When I do, the jars and the water and the cork inside the jars are going to begin to move in a circle. What we know about objects moving in circles is they experience an inward force and an inwards acceleration. Now what's going to happen here is the object that has the most inertia inside the jar is going to be the object that resists the acceleration the most. And that happens to be the water. On a per milliliter basis, it has the most mass, and thus it has the most inertia, and it resists that acceleration the most. The cork, on the other hand, resists the acceleration the least. Therefore, the cork's going to lean in the direction of the acceleration, giving us evidence of that big idea in physics, that objects that move in circles experience an inward or a centripetal acceleration. Here we go. There you see it. The corks are leaning towards the center of the circle. The water is resisting that acceleration the most. The cork resists the least. You have inwards acceleration as evidenced by that inwards lean of the cork. You got to believe in physics.
Gotta believe it. So, you have seen that centripetal acceleration results from a change in direction, and in circular motion, an acceleration due to a change in speed is called tangential acceleration. So to understand the difference between centripetal and tangential acceleration, consider a car traveling in a circular track. Because the car is moving in a circle, the car has a centripetal component of acceleration. But if that car's speed changes, the car also has a tangential component of acceleration. Now let's look at solving centripetal acceleration. We have a test car that moves at a constant speed. Again, that's what we were looking for, that term, constant. Around a circular track. If the car is 48.2 meters from the track center and has a centripetal acceleration of 8.05 meters per second squared, what is the car's tangential speed? So what do we know? We know that the radius between the car and the track is 48.2 meters. That the centripetal acceleration is 8.05 meters per second squared. We are trying to solve for the tangential speed. And so taking the formula that we saw a few slides ago, apparently it's going to take forever to get there, we rearrange it to solve for VT, remembering that VT is squared. So you'll have to remove that square and use the square root. So you take your acceleration, your 8.05, multiply it by your your radius, and then take the square root. You'll have a tangential speed of 19.7 meters per second. Pretty simple, but I still want us to open up our books to page 236. 236. Okay. So on page 236, let's look at number 3. A dog sits 1.5 meters from the center of a merry-go-round. The merry-go-round is set in motion, and the dog's tangential speed is 1.5 meters per second. What is the dog's centripetal acceleration? What is, I didn't flip it. There we go. All right, so first things first, what do we know? We know that the radius is, not zoomed in far enough, 1.5 meters. No, just kidding. What was it? Yeah, 1.5 meters. And the tangential speed is 1.5 meters per second. We need to solve for the centripetal acceleration. So we simply just take our formula as is. AC is equal to VT squared over R. So we get 1.5 meters per second squared divided by 1.5 meters. What is my centripetal acceleration here? There you go. 1.5 meters per second squared. Let's do one more. Let's look at number 4. Okay. Let's look at number 4 here. A race car moving along a circular track has a centripetal acceleration of 15.4 meters per second squared. If the car has a tangential speed of 30.0 meters per second, what is the distance between the car and the center of the track? So again, what we know is the centripetal acceleration of 15.4 meters per second squared. If tangential speed is 30.0 meters per second, what we don't know is the radius. So we're going to rearrange this to have our radius is equal to VT squared divided by centripetal acceleration. So go ahead and plug in your numbers here. We've got 30.0 meters per second. And square that divided by 15.4 meters per second squared. $58.4. What's your unit? Meters. Simple. That's how today's homework's going to be. Those of you at home, I'm going to post the homework here in just a few moments. but you may go ahead and sign off. Oh, actually, you're going to be doing all 10 questions. Okay? No removals. All 10 questions. Mhm. Yep.
Mr. Dorfman, who these turned in online or last month?
You can turn them in person. Yes. Unless the other units are in other labels as well, which you can relate to that, as long as they're all the same, but typically they're in meters.
Thanks.
Uh-huh.